Good morning, Math 30s. This lesson is going to finish off our unit on transformations. So this is going to be part one of two parts. The lesson is on the inverse of a relation. It corresponds to the workbook lessons 6 and 7. Now in the workbook, I will be assigning these two lessons for their homework. The notes for this lesson though is not in the workbook, it's just in my note package on the Google Classroom. Okay, before we get into the concept of what is the inverse of a relation, we're going to relate this to something that we previously learned in lesson 2, which was reflections. So the inverse of a relation, it has to do with reflections. Now in lesson 2, I introduced vertical reflections and I introduced horizontal reflections. So remember that a vertical move is an up down move and a horizontal move is a left right move. Okay, so if I give you a point on a graph, and let's say that point was 3 comma 4, and I say have that point undergo a vertical reflection, that point will be reflected and the new coordinate would be 3 comma negative 4. Now the x-axis here acts as the mirror. So what we say is we say that this point was vertically reflected in the x-axis or about the x-axis. A couple of things with vertical reflections. Remember that y becomes negative y, right? So this 4 becomes negative 4. And the other way that we're going to tell a vertical reflection is if I give you the function y is equal to f of x and I say have this undergo a vertical reflection, well, we're going to take out y and we're going to put in negative y. So negative y is equal to f of x. If you solve for y, so divide both sides by that negative 1 to isolate y, what we would get is y is equal to negative f of x. So if you see this, that means that y became negative, right? So y went to negative y, and this is a vertical reflection. The second type of reflection we did was a horizontal reflection. So if I take that same coordinate, 3 comma 4, so let's pretend that's 3 comma 4, and I say, okay, reflect this point, have this point undergo a horizontal reflection. So horizontal means this would be a horizontal line, right? A left-right move is a horizontal move. So that point would bounce over here. The mirror line would be the y-axis, and the new coordinate would become negative 3 comma 4. So what you should see is the replacement notation is x goes to negative x. So for horizontal reflection, x goes to negative x. Okay, that would be a um, that represents a horizontal reflection. X goes to negative x. So then in our function notation, if our original function was y is equal to f of x, what we are going to do to show that it's undergoing a horizontal reflection is we need to take out the x and I need to put in a negative x. So y is equal to f of negative x. So if the negative is inside the function, that's going to represent a horizontal reflection. Okay, now the last type of reflection, I introduced it in lesson 2, but I said, okay, we will actually get to that in the last lesson, which is this one here, lesson 5. So the last type of reflection, we've got vertical is number 1, horizontal is number 2. The third type of reflection, it's a reflection in the line y is equal to x. Okay, so what that means is the following. If I give you a coordinate, okay, so xy, and I say I want this coordinate reflected in the line y is equal to x, this is what is going to be called the inverse of a relation. Okay, so the inverse of a relation. And how the inverse of a relation is found, it's found by interchanging the coordinates, the x and the y coordinates. So again, if I give you a coordinate x comma y, and I say, what is the inverse of that coordinate? You interchange the x and the y to y comma x. So here's what I mean. Take that point 3 comma 4. So I'm just going to erase this. Okay, so when we're finding the inverse of a relation, we're given a point, x comma y, and to find the inverse of this point, you simply interchange the coordinates, so it's going to be y comma x. So interchange those two, and it's going to be y comma x. So in the original function, if I give you 3 comma 4, so let's draw this. 1, 2, 3, 4. 1, 2, 3, 4. So 3 comma 4 would be right here. Okay. Now, the inverse of that point is going to be 4 comma 3, which would be right here. So these are inverses of each other. And you might say to me, okay, well, how are these reflections of each other? Where they're actually reflections of each other, they are reflected in the line y is equal to x. So if I draw the line y is equal to x, so here's y is equal to, I've got x in there. So this is the line y is equal to x, right? Here's the table of values for y is equal to x, 1, 1, 2, 2, 3, 3. So it's a straight line. So this line here is the line y is equal to x. And this coordinate here, which was 3 comma 4, it is reflected in this line y is equal to x. These two are mirror images of each other in this reflection mirror line here. Okay, so this is how we're going to find the inverse of what's called a relation, and we do that by interchanging our x coordinates and our y coordinates. So let's look at an example. Okay, so let's look at a nice example. It says, consider the graph of the relation shown. So this is a graph, and remember from Math 10C, all graphs are called relations. And then some graphs are functions and some graphs are not functions. And we'll get into what a function is today. I'll review that from Math 10C. This graph is a relation, so all graphs are relations. This graph would also be a function, okay? So just to quickly review what a function was from Math 10C, do you guys remember we did something called the vertical line test? So if I give you a graph, so this graph here, and I say, okay, is this a function? What you did in Math 10C is you drew a vertical line. And if your graph only cut the vertical line at one spot, this relation is also called a function. So this graph, no matter where I draw this blue vertical line, it will only ever cut through the graph once. So this relation is also called a function. I'll give you an example from 10C of a graph that we would have done that was not considered a function. So in 10C, so let's say I said this graph here. So this is a relation, this triangle, it's a graph, it's a relation. Is this a function? You would have done your vertical line test and you would have said, no, this fails the vertical line test, so this graph is not a function, right? Okay, so this graph is a function, and what we are going to do is we are going to graph the inverse of this, right? So we're going to reflect this graph in a line y is equal to x. So we're going to draw the inverse of this. And then we're going to see, is the inverse graph, is that a function? Okay, so let's do that. Let's label our points. So it's really important when we do inverses because points can move to, it could look really messy. So we'll call this A, B, C, D, E, and F. And this is the points on my original graph. And on my inverse graph, what the points are going to be is y comma x. Actually, one thing I also want to show is this is my original function here. So I'll write it below. This is y is equal to f of x. How they show that they want the inverse of a relation is you simply interchange x and y. So the inverse equation is x is equal to f of y. So if you get a graph like this is f of x, and if they say, okay, please show me x is equal to f of y, what they want is the inverse graph. So they want you to interchange the x and the y values. Okay, so what would this be? A prime is going to be 4 comma negative 6. You just simply switch that. B prime is going to be 6 comma negative 4. C prime is going to be 6 comma 0. D prime is going to be 2 comma 2. So let's star this. This is going to be our invariant point, and I'll talk about on inverse relations where the invariant point will lie. E prime is going to be interchange 2 comma 4, and F prime is going to be 0 comma 6. Okay, let's get this new graph in. So A prime is 4 comma negative 6, would be right there. B prime is 6 comma negative 4, would be right there. C prime is 6 comma 0. Oops. C prime. D prime is 2 comma 2. And sorry, I just lost my train of thought for a second. 2 comma 2 is D prime. E prime is 2 comma 4. 2 comma 4. Is that right there? And 0 comma 6 is this point right here. And that's F prime. Okay, so let's get a ruler, different color. And let's connect A, B, C, and D. So A to B, B to C, C to D, D to E, and E to F. Okay, I'm going to erase now my letters. And the last thing we need to put in is we need to put in the line y is equal to x. So we always, for inverses, we want to show our line of reflection. Okay, so what I'm hoping that you could see is that, for example, this coordinate here, which was negative 6 comma 4, that point is reflected to here, 4 comma negative 6. And these 2 points are reflections of each other in the line y is equal to x. Okay, so these 2 points are reflections of each other in the line y is equal to x. Now, so this is our original graph, was the original black graph, and our inverse graph, which is our blue graph, is x is equal to f of y. Okay, so that's our inverse graph. So these two are inverses of each other. So let's write that down. So these two are inverses of each other. Okay, so we've got the line y is equal to x drawn, and the pattern that you should notice is that the points are reflected in the line y is equal to x. So negative 6, 4, the reflection of that point would be 4, negative 6. So the pattern is reflected in the line y is equal to x, okay? And are there any invariant points? What I want you to key in on is this point right here. So if your original graph cuts through um, the line y is equal to x. So if your original graph is on the line y is equal to x, your inverse graph will also have a point on that line as well, that exact same point. Okay, so I'll show you that with the next example. So 2, 2 was our invariant point, and star any point on the line y is equal to x, right? And the reason is 2, 2 on the original point is going to be 2, 2 on the reflected inverse, okay? The last thing, I sort of added this in. This is pretty important. You might want to write this down. So interchanging the x and the y coordinates on the graph of a function. So again, if we have the graph of a function, y is equal to f of x, and if we interchange the x and the y coordinates, so x is equal to f of y, so we interchange the x and the y coordinates, what we have just done is we've produced a graph that is a reflection through the line y is equal to x. So these two graphs would be reflections of each other in the line y is equal to x. And the resulting graph is the inverse graph. So this is the inverse of the original function. Okay? And that's pretty much stating that right here. Okay, let's look at this question here. So here's the graph of y is equal to g of x. Okay, so y is equal to g of x. And what A says is sketch the graph of its inverse on the same grid. So if we're given y is equal to g of x, the inverse of this would be interchange the x and y. The inverse would be x is equal to g of y. So that's what we're going to graph. X is equal to g of y. Okay? And my original points, x comma y, on my inverse graph are going to be y comma x. So that's how we're going to find them. Okay, so let's take our original graph and points from our original graph. So y is equal to g of x. Let's take these points here. So we'll call that A is at negative 4, 4. B is going to be at negative 1, negative 1. C is going to be at 1 comma 3. So this guy here. And D is going to be at 3 comma 2. Okay, the inverse of this graph, so the inverse of that function is going to be x is equal to y, nope, x is equal to g of y, sorry. And the inverse points, so A prime, B prime, C prime, and D prime, are going to be 4 comma negative 4, negative 1 comma negative 1. So that's going to be my invariant point. 3 comma 1 and 3 comma 2. Okay, from here, nope, sorry, this guy is wrong. This guy's 2 comma 3. Okay, let's get our new graph written. So our new graph is going to be A prime is at 4 comma negative 4. So A is going to join to B. So A is going to join to B is going to join to C prime, which is 3 comma 1. And this should be done in a ruler, but I'm going to actually end up erasing this because I want to show you something at the end. So that's why I'm not doing that in a ruler, but you guys will do yours in a ruler. And d prime is 2 comma 3. 2 comma 3 is here. Okay. Now, something off. Why does this look off? 4 comma negative 4, negative 1, negative 1, 3 and 1. Oh, this point. What am I doing? Sorry, I was like, something is not right here. Negative 1 goes there. So A to B to C, there we go. That looks like it's reflected. And then if I get my reflection line in there, so my reflection line is in the line y is equal to x. So that's the reflection line. This would be the graph. This blue graph is the graph of my inverse, okay? So that would be the graph of x is equal to g of y, is this blue graph here. So A we've done. Sketch the graph of its inverse on its same grid. B, is this inverse a function? So if we look at this blue line exclusively, is this a function? And I hope everybody would say it is not, right? It fails the vertical line test. So the answer is no. Let's sort of show where it's no. Here it would fail twice. Here it would fail 3 times. So the inverse is not a function. And we'll write fails vertical line test. We're going to do C quickly, and then what I'm going to do is I'm going to erase my graph, and I'm going to show you another way that you've never been taught before, something called the horizontal line test that we're going to apply to the original function. And you could actually figure out if the inverse is going to be a function without even drawing it by applying this horizontal line test, but we'll do that after. So C says, state the domain and range of the function and of the inverse function. Okay, so here's my function here, the green. So the domain of the green was, my domain was from -4 to 3, right? That was my domain. So my domain was -4 to 3. That should be a square bracket. So -4 to 3. And the range of my original function, the range of this guy, the biggest y value was 4. And the smallest y value is down here at -1. Okay. Now what I want you to do is I want you to see if you could figure out the domain and range of the inverse. And there's something interesting is going to you should notice with the domain and ranges. Okay, so let's do the domain and range of the inverse function. So the domain was blue, so the biggest x value was 4, smallest was -1. So domain -1 to 4. And the range of the blue, so my graph is getting really messy, but the range of my blue was from -4 to 3. So -4 to 3. What you should notice, and this is what's going to be in the next couple slides, is that the domain of your original is the range of your inverse. So the domain of your original is the range of your inverse. And the range of your original function just happens to be the domain of the inverse. So again, the domain of the original is the range of the inverse. The range of the original is the domain of the inverse. That will always happen for inverse relations. So essentially what I could do on a test is I could give you the domain and range of a function, not even give you the graph of a function, right? So on a test, I could basically say, okay, you're given an original function, y is equal to f of x. And let's say on a test, I say the domain of the original function is -5 to 10. I could ask you this on a test. I could just say x, f of y, and then I could say, what's the range? And you just need to be able to look at this and you need to be able to say, okay, the transformation that this is an inverse, right? Because she interchanged x and y. The domain of the original is going to be the range of the inverse. And you'll be able to do that. Okay, before we go on to the next example, you guys, I'm going to erase this. I'm going to erase all of this. And I'm going to show you, I'm going to write something called the horizontal line test. So just write HLT. It's going to be on the next slide, but I just want to introduce this over here. Without even graphing the inverse of this, I can look at this graph and I know without graphing the inverse that the inverse will not be a function. It will fail the vertical line test. And what I could apply to this graph, it's something called the horizontal line test. So if the original graph, if you draw a horizontal line through the original graph, if it cuts more than 2 points, this graph, the inverse will not be a function. The original fails the horizontal line test, so the inverse will not be a function. So I'll give you like a couple other examples. So let's just say I gave you this graph here, a straight line. Or sorry, that looks like y is equal to x. Let's say, I'm just trying to think of a graph. Okay, so this line here, this straight line. If I said, would the inverse of this be a function? What you would do is, this is the original graph, you would apply the horizontal line test. So the horizontal line test, if I draw horizontal lines through this original graph, it passes. That means that the inverse of this blue line will be a function, okay? If I give you a parabola though, which we're gonna look at later on, and I say, is this parabola, is the inverse of this parabola going to be a function? The answer is no. The inverse will not be a function because it fails the horizontal line test. So the inverse of this green line, it would look something like this, and that red line is not a function. Okay, so something called the horizontal line test. Okay, domain and range of inverse functions. So this is what we just talked about in the last example. And basically what it's saying is the domain of the original function, right, is going to be the range of the inverse. So the domain of the original is going to be the range of the inverse. And the range of the original, that's the original function, is going to be the domain of the inverse. So just to illustrate this again, y is equal to f of x. If it undergoes the transformation and it's an inverse relation, we're going to have x is equal to f of y. So let's say I give you the domain of this guy, and I say that the domain's from -3 to 2. So -3 to 2. And I give you the range of this guy, and let's say the range is from -6 to 8. Okay. If that's on the original function, the domain and range, then the domain on my inverse graph is going to be -6, 8. And the range on my inverse graph is going to be -3, 2. So the domain on the original is the range on the inverse. The range on the original is the domain on the inverse. Okay, applying the horizontal line test. So again, it says sketch the graph of the inverse of the relation. I'm not going to sketch the graph. What we're going to do is we're just going to look at the original graphs and we're going to decide, is the inverse going to be a function? So the inverse is a function if it passes the vertical line test, right? That's when the inverse of is a function. But just looking at the original graph, we could apply something called the horizontal line test. If you draw a horizontal line through the original graph and it cuts through more than one point, then the inverse will not be a function. So this fails the horizontal line test. Therefore, the inverse, which is x is equal to f of y, will not be a function. Okay. I don't really like this example. I wish they would have given a different example for this. They basically gave you a straight line, and they're like, if you draw the inverse of this line, and we actually will do this one, we'll draw the inverse of this one. If you draw the inverse of this line, would it be a function? Well, if this is my graph, I could essentially draw my horizontal line going right through it, which is going to touch all the points on that graph. So the answer is going to be no, the inverse is not going to be a function. But let's actually draw this one. So if I pick points on my original graph, this is -4, 2, right? So -4, 2. The inverse is going to be 2, -4. So x is 2, y is -4. So it's going to go there. And then let's say I pick this point. So -2, 2. -2, 2. Well, the inverse of that will be 2, -2, which would be right there. And then let's say I pick this point, which is 4, 2. 4, 2. The inverse of that is going to be 2, 4, which would be up here. So what I've done is this is my new graph. That's a straight line. That graph would definitely fail the vertical line test, right? If I draw a vertical line through there, it passes through all the points. And then let's draw a reflection line. So let's draw our line y is equal to x. So there. And again, these points are reflections of each other in the line y is equal to x. Right? These are exact reflections of each other. So again, the original, the inverse of both of these functions would not be functions. They would be relations, right? The inverses of each of these would fail the vertical line test because the original functions fail the horizontal line test. Okay, there's the last concept that I want to cover in this video, and then I'll do, I think, yes, part 2 will be the last 2 examples. So we're going to talk about, there's a new notation for inverse notation. So y is equal to f of x, that's function notation, right? That's our original function. So when we take the inverse of this function, there's 2 different ways to write it. So y is equal to f of x, that is our original function. And when we do the inverse, it could be written as one of 2 ways. You'll see it on the diploma or on homework questions. They could say, please write that as x. They could express that as x is equal to f of y. So if they've interchanged the x and the y, you know that this transformation is an inverse, okay? The other way that they could show you that they want you to do an inverse is they could say, okay, here's your original function, y is equal to f of x. And then they could say, please have it undergo this transformation. Y is equal to, y is equal to f inverse of x. So if you see this notation or this notation, these are both inverse notations, okay? Now, from grade 10, sometimes students want to look at this and they want to say, oh, isn't that like f to the negative 1? Because it looks like that from exponents. No, this right now, because it's tied to your function. This is just how we denote in math that it's an inverse of a function. And how we read this is you would say f inverse. So if you see that applied to your f, that's the inverse function, and it's read as f inverse. Now, if your inverse is function, this is how we could write it. So if your inverse is a function, your inverse is not a function. The inverse fails the vertical line test. This is how we would write the equation of the inverse. Okay, so this is how we would show it if it's not a function, if the inverse is not a function. And I'll show you two examples that we're going to do. One's going to be the inverse as a function and one is not going to be a function and how we would show that. Okay, so what this question says is it says determine an equation for the inverse of a function. So the inverse of a function, we know that x comma y, this is my original equation here. What they want to know is what's the equation of the inverse. Simple to do. You interchange x and y to y plus 9. So this is the equation of my original. And to find out the equation of the inverse, we interchange x and y. Now, I can't graph this blue inverse on my calculator just yet because I need to solve for y. So let's solve for y. Subtract 9 from both sides. So x minus 9 is equal to 2y. And then divide both sides by 2. And what we would get is y is equal to x minus 9 over 2. I'm going to show this to you on your calculator. And I just want to choose the right color. So red and black. Okay. So this is going to be equation, and this is going to be equation of the inverse. What we are going to do is we are going to see, is this a function? So this is my original. Is this guy a function here? So let's graph this original in your y1. So let's graph the original. And actually, I'm just going to clear this x for now. I'm going to graph it in y2 because I'll make it red. So the original is 2x plus 9. So let's look at the graph. You should just recognize that this is a linear function from Math 10C. It's a straight line. Does this pass? So this is a function, right? But in order to figure out if its inverse is going to be a function, does this guy pass the horizontal line test? And it does. So when we draw the inverse of this, it is going to be a function, right? So when I draw this equation here, that's the equation of the inverse, it's going to pass the vertical line test now. So let's put this in our calculator. And remember that I want my numerator in a bracket. So x minus 9 in a bracket divided by 2. So y is equal to, I'll do that in black, open bracket, x minus 9, close that bracket, divided by 2. There's the graph of the inverse, and this is a function. This inverse passes my vertical line test. Let's actually draw our reflection line. So let's draw the line y is equal to x so that we could see that it is in fact a reflection. Look at this, your original graph cut through the reflection line. So remember that's your invariant point as well on your inverse graph. So that's an important point. And these are reflected, the red line and the black line in the line y is equal to x. Now, because this inverse is a function, how I could write the proper notation would be f negative 1 of x. So f inverse, right? That's how we read this. F inverse of x is equal to x minus 9 over 2. That is the equation of the inverse. That's the equation of the inverse. Okay, let's do this guy, x squared plus 5. So let's look at the original graph first. So go to your calculators, go to y is equal to, let's clear these. And let's look at the original graph first. So the original graph is x squared plus 5. X squared plus 5 graph. Okay, it's a parabola. This parabola, when we reflect this in the line y is equal to x, is the inverse of this going to be a function? So hopefully you guys are realizing now you could just look at this. If I apply the horizontal line test to this, it's going to fail. If your original graph fails the horizontal line test, the inverse will not be a function. Let's prove that. Okay, how do I write the equation of the inverse so I could actually graph the inverse? I want to graph the inverse of this guy. So what we do is we interchange x and y. X is equal to y squared plus 5. We solve for y. X minus 5 is equal to y squared. In order to get rid of a square, you square root. Now, when you square root both sides, this, remember, is going to be plus or minus. So just to show you over here, let's say I had y squared is equal to 25, and I said, well, what's y equal to? If you square root this and you square root this, y is equal to plus or minus 5, right? So remember that when you square both sides of an equal sign, you have to take the positive and negative case. Okay, so I'm going to just erase that. So the square root of y squared is y. It's equal to plus or minus x minus 5. And I'm just going to rewrite this as y is equal to plus or minus x minus 5. So this is the equations of my inverse. Y is equal to x plus 5 and y is equal to x minus 5. Maybe I'll write that. Y is equal to the square root of x minus 5 and y is equal to the negative square root of x minus 5. Okay, if I graph these two, I'm going to get the inverse of this guy. So let's do that. Y is equal to, let's do the square root of x minus 5. And I'll show you what that will look like, right? So that is going to be just half of my graph reflected. So now we got to do the other half. And the other half is the negative square root of x minus 5. Graph that. There we go. So this graph here is the inverse of this graph here. They're reflections in the line y is equal to x. So let's illustrate that. So, and you could check, right? So the vertex of this parabola is 0, 1, 2, 3, 4, 5, 0, 5. This would be 5, 0, right? These are reflections of each other in the line y is equal to x. Now, my inverse though, this graph here is not a function. It fails the vertical line test. So because this inverse is not a function, I'm not going to write the inverse equation as f inverse x. I'm not going to do that because this is not a function. So I'm just going to keep it starred as, or I'm just going to keep it as y is equal to plus or minus the square root of x minus 5. Okay? And that concludes part 1. Part 2 will have the last 2 examples, which is on restrictions on the domain of a function.